All right, let's dive right in. We're going to take a journey into the very stuff our world is made of, solids. I mean, from the phone in your hand to the salt on your kitchen table, they all have this secret life, right? A hidden, microscopic world of structure and chaos that basically defines everything about them. And it all starts with a really simple question that uncovers a huge difference.
So think about this for a second. Have you ever really wondered why a tiny grain of salt, if you look at it up close, forms a perfect little cube, but a piece of glass just shatters into a million random, shapeless pieces? What's the deal with that? Well, the answer is hiding deep down in how their atoms are arranged, and that's exactly the mystery we're going to solve today.
You see, at the absolute heart of this question is this fundamental split in the world of solids. It really all comes down to a battle between perfect, repeating order on one side and complete, jumbled-up randomness on the other. This is the first, most important key to understanding everything else.
And you can see these two sides perfectly right here. On one side, for crystalline solids, look at that diagram. It's that perfect, long-range order. Every single particle knows its place in this beautiful, repeating pattern. But then you look at amorphous solids, like glass, and it's basically a microscopic mess. The particles are just frozen in place in a totally random jumble.
Now, this difference on the inside has massive consequences on the outside. Crystalline solids, because they're so perfectly structured, have these sharp, super precise melting points. They're also something called anisotropic, which is a fancy way of saying their properties, like how they bend light or conduct electricity, can actually change depending on the direction you measure them. Amorphous solids, though, they just kind of soften and melt over a whole range of temperatures. And they're isotropic. Their properties are the same no matter which way you look. So, how in the world do crystalline solids pull off this incredible perfection? Let's zoom in even further, way down to the atomic level, and check out the blueprint that makes it all possible. The secret, the absolute key, is something called a unit cell. And what's so cool about this idea is how simple it is. The unit cell is just the smallest possible repeating piece of the crystal. Seriously, it's like the single Lego brick that when you stack it over and over and over again in every direction builds the entire magnificent castle.
So, let's meet the simplest Lego brick in the box, the simple cubic unit cell. And it is exactly what it sounds like. It's just a cube with a single atom sitting at each of its 8 corners. That's it. It's the most basic starting point you can have for building a crystal.
Okay, let's level up. Next, we have the body-centered cubic, or BCC cell. It starts with the same 8 corner atoms as the simple one, but then, like the name says, it adds one more for good measure, smack dab in the dead center of the cube.
And the last common one we'll look at is the face-centered cubic, or FCC structure. Again, we've got our 8 corner atoms, but this time we also pop an atom into the center of each of the cube's 6 faces. Now keep this one in the back of your mind, because it's going to be a really big deal in just a minute.
So here's a tricky question. How many atoms does each of our little Lego bricks actually contain? This is where it gets really clever. You see, an atom on a corner is actually shared by 8 different unit cells, so each cell only gets 1/8 of it. And an atom on a face is shared by 2 cells, so each gets half. So when you do the math, that simple cubic cell only has 1 total atom inside. The BCC has 2, and the FCC has a grand total of 4 atoms. Now, why do we even care about all these different arrangements? Well, it boils down to one word: efficiency. Nature is all about efficiency. The way these atoms are packed together determines how dense and how stable a solid is going to be. It's all about using space as effectively as possible.
And the process for building one is actually pretty logical, you know? You just start by lining atoms up in a one-dimensional row. Easy enough. Then you stack those rows to make a flat, two-dimensional plane. And finally, you just stack those planes on top of each other to build the whole three-dimensional crystal. And the efficiency of these different stacking methods? Well, it varies wildly. That simple cubic structure we saw first is, honestly, it's pretty wasteful. It leaves a lot of empty space, with only about 52% efficiency. The body-centered cubic is a lot better, clocking in at 68%. But the face-centered cubic, the one I told you to remember, that one is a true champion. It packs those atoms in with an incredible 74% efficiency. There's a reason it's so common in nature.
But okay, here's the plot twist. All this talk about perfection, these perfect lattices, it's just an ideal. In the real world, no crystal is truly perfect. And what's amazing is that it's these flaws, these little imperfections, that often give materials their most useful and interesting properties.
And don't just take my word for it, the source material puts it plainly.
Imperfections are not the exception. They are the rule. These defects aren't mistakes. They are a fundamental part of what makes a solid work.
So let's look at a common one. On the left, you've got your perfect, idealized crystal. But on the right, you have what's called a Schottky defect. What's happening here is that a pair of oppositely charged ions are simply missing. They've up and left their spots, creating these empty holes, these vacancies in the lattice, but the whole crystal stays electrically neutral.
Another common flaw you'll see is the Frankel defect. Now, this one's a little different. In this case, an ion, usually one of the smaller positive ones, doesn't leave the crystal. It just pops out of its proper spot and squeezes into a tiny space between the other ions. So it's not a missing worker, it's just a displaced one.
Okay, so we've got structure, we have efficiency, and we even have flaws. How does all this microscopic detail actually connect to the world we live in? Well, it's the absolute foundation of all modern electronics, and it all comes down to how these structures affect the flow of electrons.
It's all about something called band theory, basically how easily electrons can move around. In a conductor, like a metal, the energy levels where electrons normally hang out, that's the valence band, actually overlap with the energy levels they can move into, the conduction band. There's no gap. It's like an open highway, so electrons can just move around freely, which is exactly why metals conduct electricity so well.
Now, an insulator, like rubber or glass, is the complete opposite. There's a huge energy gap between those bands. It's like a massive canyon that the electrons just don't have enough energy to jump across. So they stay put. No current can flow. Simple as that.
And then you get to the magic ingredient, semiconductors. Here, the band gap is small. It's not zero, but it's not massive either. It's just right. With just a little push, maybe from some heat or a bit of voltage, the electrons can make the jump. And this allows us to control the flow of electricity with unbelievable precision.
And the coolest part is we can actually tune this property through a process called doping. By adding just a tiny impurity, we can create what's called an N-type semiconductor, which has extra negative electrons ready to move. Or we can create a P-type semiconductor, which has holes that act like positive charges for electrons to jump into. This whole N-type and P-type thing, that's the basis for every single transistor and computer chip on the planet.
And that brings us all the way back around, from the perfect cubic shape of a salt crystal to the chaotic jumble of glass and the perfectly controlled world of silicon. It all comes down to the secret life of atoms. So the next time you pick up a simple grain of salt, just remember, you're not just looking at a thing. You're looking at an entire universe of perfect,